Okay, so we are back with the lecture of your favorite lecture, right? 3rd of June is the exam. And do you remember what is the only requirement to take part in this exam? Complete teaching survey, right? Okay. Right, and the teaching survey is today. So please complete it. If you do, we don't have a problem. If you don't, then we have a problem, because that means I will set your points to 0 in the exam. The location is to be announced, but we will probably be coming here in PCO2. And I already instructed the teaching assistants to book the room next door. So it will be the same setup on location as for the midterm. Okay, so we go back to eigenvalue problems and nonlinear equations. And we already saw what's an eigenvalue problem. That is given in the form given here. A matrix times a vector equals an eigenvalue times a vector, where the matrix is just a transformation that takes a vector and projects it on, it doesn't change the direction, right? But just leads to a compression or stretch. Right, and for the non-linear equations, we said sometimes there are problems that are simple to solve, then solvers are implemented, and sometimes the problems are a little bit more complicated, and then it is very hard for us to find a solution. So we discussed finding the root of a function by plotting. This is always an option. So we basically need to decide which area we want to visualize. Then we tell Python, yes, please, this is the function, do the plot, and then you can read the values from the plot. Be very careful with artificial parts here. Artificial means they're not actually there. It's because there are some mistakes. Here in the example F1, the artificial line is the vertical lines at roughly, what is that, pi half, plus and minus. So here minus 1.7 something and plus 1.7 something, right? Because we checked this with a different type of plot, scatter, then we didn't have these lines anymore. There are benefits and disadvantages for plotting root finding. It's possible resolution errors, right? Plus it's some tedious work that we see in F2. So then we discussed the bisection method. Do you remember the bisection method? Some people say bisection, sometimes say bisection. So it means we take a function where we define a start and stop search interval. We divide this in two. We're looking for a change of sign. And if we find a change of sign, we take this interval as a new start and stop interval. We split the interval in half, and we do so until we reach a required accuracy. So far, so good? So what you need to do is you need to choose a reasonable size of your epsilon, where the epsilon is the solution accuracy. Because whatever we do in the bisection method, we don't define a point, we define an interval from A to B. So here in short is the bisection algorithm given again in a particular form following one interval. You see this here by the choice of FA, FM. If the change of sign would be in part B, then the interval would change to FM and FB. Important to note is it's an iterative solution. We need to have certain iterations. An iteration is something we do all over again and again and again and again. And we have done this in 4 loops already. Do you remember the 4 loops? We have a for keyword, then we have an iterator, then we have in and a sequence. That was the general syntax. Right? An iterator runs over different executions of the loop body, taking different values. So here we find again the word iterator. It's highlighted in bold font for you, so you can see it very clearly. Okay, so we already implemented the bisection method, and it's a very, very simple implementation. So the bisection method can be implemented in just a few lines of code. Next, we're going to talk about Newton's method. Note that the bisection method is just one possible equation solvers. There are many more equation solvers. In fact, you can come up with your own. However, some of them work better for some tasks, some of them work better for other tasks. So that is where we would normally put a benchmark, a comparison between the capability and limitations of different algorithms. So in the Newton method, we basically try to make use of a gradient of a function at a point to get a guess or a more educated guess for the next possible value in our iterations. For example, look here. The first equation, xk plus 1 equals xk minus f of xk divided by f prime of xk. Here, xk is a point on the x-axis. And indeed, it's the kth point. When I tell you it's the kth point, that means we start from k0, then we have k1 as the next point, followed by k2, 3, 4, 5. Right? And the kth point is just one of many. However, k is an integer. Right? It basically counts how many points we have done already. And that note, xk plus 1, tells us so the next position on x is given by x, and this is the place where we are at the moment, our current location, and then the function value divided by the value of its derivative. So far, so good. So how do we know that this is useful? Well, it comes from the definition of the derivative given here, f prime of x equals df over dx. You know this from high school. And the Taylor expansion where f of x plus dx, that reads, oh, we are at a location x, and now we look at a very, very small change next to x. So we take a tiny step into dx. Yes? So we want to only move a tiny bit forward. Now, this can be written as f of x plus dx times the derivative. If you would like to verify this, then you can try implement this in Python with SymPy to see what comes out, okay? Okay, so when we reorder this a little bit, so then we actually can restore the value over here. One thing I want to notice. Well, is a little bit wonky here today, right? But that's not what I want to highlight. There's a big difference that you must be aware of between x and xk. For the case x, x is a continuous variable, right? That any value of x is possible. X of k, right, is a set of x values or list of values that you have chosen discretely. You need to choose your starting point. That can be any value, but the next values are only given by this particular formula. Right? So it's a little bit different. Well, this little bit is actually a big difference. So just make sure that you know the difference. Okay. Before we go further on, do you think you can restore this information from this equation? Restore this one by reordering the third line? Can you do that? Who thinks who can do it? Who's confident? Who thinks who cannot do it? Here, I want to that you take this one and show me that you get this one. Do you think you can figure it out? Yes. I see some head nods. Do I see head shake somewhere? No? One head shake? Do you want a hint? Definition of dx. Dx is x2 minus x1, right? A very, very small difference. We plug this in and then, well, x2 is what? x1 plus 1, right? Not x1 plus capital 1, but the index 1 plus 1, right? It's the next, okay? So if you put in k1 here, right, then x1, and then this one here would be x1 plus 1, right? Okay, so try this out, reorder, you will find it, I'm pretty sure now. Okay, but this is basically the trick. Okay, so next one. That's one of the tricks. Next one. We need to implement this. In particular, we need, well, a few things. We need a choice of x. We need to evaluate the function value at f of x. We need to get the derivative of f of x, right? Evaluated at that point. And then we get the next. So actually we need 1, 2, 3 ingredients, right? So far so good? Yes? Okay. So now, how would we design an algorithm for this? So first step, select a point xi. So if we start, then we select x0, right? Next point, obtain the derivative f of x at xi. So we need to get the derivative, plug in xi, and this we call m. We call it m because it's on the intermediate point. or inclination, right? However you want to call it. So actually it's the inclination at that point, or we would store it as a variable. Okay, and then we get y equal mx plus n. But this is just a linear function. And when we have this function, we can find the root xi plus 1 of this linear function, and we call this xi, we override the xi with a new xi plus 1. So far, so good? Yes, no, maybe? Okay. So here's an example. This is any function, f of x on a plotted f over xx. X, yeah. Okay, so we choose, step 1, we choose an xi. We get the function value, right? Then we calculate the derivative. D over dx f of x evaluated at x equal xi. And when we have now the linear equation, we actually can follow this and find when it is 0, right? The root. And the root would be our xi plus 1. So far, so good? Yes, no, maybe? Okay. So if we have the new point, we would do the same thing again, right? We don't need to choose a function value anymore. The algorithm gave us one. We are evaluated f. We find the inclination or the derivative evaluated at this value. We do the linearization and we calculate the next possible function value, the next possible root, which would be here now. And then we do this again and again. And we slowly go to our best obtainable root of the function. So now in Python, so what do we do? So here I import SymPy as sp and I define a tolerance that I want to have for my accuracy. Yes, so far so good. Then I say, yes, I want to have, I define some symbols. One is my x, and the other one is actually the function I'm going to approximate here, right? So the function I want to find the root for is sp exponential of s of x minus 2. Have you seen this function before? Yes, no, maybe? Yes, right, last lecture. If you haven't, then you didn't come to the lecture, and you didn't even watch the fantastic YouTube videos, right? Okay. So you didn't even open the course book. So this is from the course book as well. So here we have now our problem defined. We want to find the root from e of should be minus no e of x minus 2. Right, and in the next part we make use of our lambdify capabilities. Do you remember what lambdify was supposed to do? Lambdify the communication between SymPy and NumPy. So with lambdify, we actually can use numerical expression, symbolic expressions and evaluate them numerically. Right, and here as a reminder is the simplify text, so the syntax given again, iterable expression and the package we want to give it to. So in our case, it would be, the function we want to have is lambda x evaluated with a lambdify. the symbol, the function, and communicate it with NumPy. So far, so good? It's a little bit advanced because I'm combining here lambda and lambdify. Do you know what's the difference between lambda and lambdify? Do you know what they have in common? So lambda is a built-in Python keyword that allows us to define a function without naming it. Right? The expression will be evaluated on call, not within interpretation. Lambdify instead is a function built in SymPy, so this is not built in, and it helps to translate a SymPy expression to another package. The variable we use here on lambdify is x, right? And that is given as argument to lambda. But in case you wonder, we have not defined x, right? We have, what was it, sx and sf indicating SymPy variables and functions, and both are expressions. And then we need a new variable to communicate with NumPy, and that is just simply x. So far, so good? Okay, so we have one lambdify with NumPy, and then we have another one here where we also use NumPy. We also have an x, we also have sx. The difference is in which function we evaluate. The function we evaluate is which one? Who can help me? spdiff. spdiff must be the difference between sx and sf, right? It's like x minus f, right? spdiff is what? Who can help me? spdiff. The method is doing what? Too long ago, right? spdiff takes the derivative of a function. So here spdiff is d over dx of f of x with respect to actually x. Not y, not z, x. Function and the derivative here. If we wanted to work with the second, oh, what was that? Everybody safe? That sounded like something dropped with water inside. Any leaks? No? Because we have a lot of PCs here, right? Plus we're on a basement level. Funny thing is, are you watching the news? There's a lot of flooding in Germany now. You know, flooding? And like 2 or 4 years ago, we had like a very bad flooding and the warning system didn't work. And all the people that lived in the basement, basically what happened is that the flood came in the night, right? So what happens is you have the doors closed because you sleep inside, right? Your windows are closed because it's cold. So the water is pushing against the doors. The water is pushing against the windows and coming in slowly, right? The water level rise. And when your feet get wet, you wake up. Oh, my feet are wet, right? But by that time, you're like, what's going on? Or it's flooding, right? Water's everywhere. Let's go out. But you can't even open the doors or windows because the water is pushing against. So yeah, you must be very, very careful. Right? And we have a lot of floods again in Germany. So be careful. Right? They're not only earthquakes and typhoons, they're also floods, especially when you travel. Okay, so back to topic. Nothing is happening here again. Okay. When you want to have second order derivative, you can either add more x variables, here an s underscore x, right? Good. So far, what do we have? We have defined a function that we can evaluate at a point, and we have defined a derivative we can evaluate at a point, right? And we can basically provide different positions on an x-axis. Here I now use x equal numpy linspace from -1 to 2.1, 10,000 different numbers, linearly spaced. So this is a very, very fine interval. Do you know what's the step size between the points? Well, that is 3.1 divided by 10,000. That is when you go from one value to the next value. Okay, so now implementing the Newton descent algorithm, right, our Newton solver. We start with a figure, but in principle we can do the plotting afterwards. The actual solver happens in this while loop. But when we define the figure first, we can keep track on what is going on in our plotting by playing around either with some print commands, some if statements to break the while loop. Okay, so what do we go? So we have here f of kx larger than the tolerance. So remember, f is a function that is being evaluated at a point, xk. And if you're very far away from the x-axis, that value is large. For example, if our function is x squared and we plug in x 100, how far are we from the x-axis? How far is the function value away from the x-axis? Well, the function is x squared. So we are 100 times 100, that's 10,000 units away from the x-axis. That's very far. What is the root of x squared? Everybody pay attention. What's the root of x squared? What's the root of a function? Don't tell me the root of x squared is x, okay? I'm not saying the square root of x squared. I want to know what's the root of x squared. What's the root of x squared? What's the root of a function? So the root of a function is its crossing with the x-axis. The root of several functions is where they cross each other, right? Where they have a common value or where they have a solution. The root of x squared is x equals 0, because the function value at x equals 0 is 0. Right? So if our value of x is 0.001, then we are, what is it, 1,000 times 1,000 is how much? 1/1,000,000 units away from the x-axis. Right? So that may be within our tolerance. And when the tolerance is when the function value is smaller then the tolerance we leave, or we don't actually enter the while loop. So our aim is to bring the function value to a value smaller than the tolerance and say this is our solution. Okay, and here's already the algorithm implemented. Xk new equals xk minus function value divided by the derivative. Do you see this? Only this line here, right? The first line under the while loop is the quasi-Newton algorithm. It's basically one line. Everything else that follows is just for plotting and visualization. Okay, but we still should discuss it. So first we plot, what is it, xk, 0, f of x, color black, line style equal dotted. And the next line, we plot x of k, f of x, so these are x and y coordinates, a black circle. Then we put a text, oh, that is my x div value, right, where we align it at the center, slightly shifted below, and then we plot from xk to xk new. From the function value to 0 and make it a green solid line. So that is our linearization, and the linear function we apply here, where we use the inclination, the descent or ascent of our function. And then we override the new value into the old variable, and we would restart our quasi-Newton. Sorry, our Newton algorithm. Yes? Get the new value, update old and new x. Do it again. Get the new value, update the new old x. We could do this by hand in principle. So far, so good? Okay, so what you don't see is actually the figure below. So let's scroll to the figure. Oh, that was our previous solution. The bisection method. Here. Here we have our quasi-Newton. So if I want to reproduce this, I need to start over here. Actually, no. It's slow. Here. Right, my tolerance defined, I execute, takes a while. My function derivative. I define my x array. I execute and make it this time a little bit larger. So 16 students here today, very good. It's like double from last time. Something is wrong. I need to import NumPy as well. And the plotting, right? You can do this over here. A little bit small still. Okay, 4 iterations, our root is 0.693. And the function value, so our inaccuracy, our deviation from 0 is 8.4 over 10,000. So this is not bad. Let me see, how do I figure size plot? That should be all right. Where is the... So I don't see why the figure is so small. Anyhow, so okay. Okay, so figure is a little bit small. Then we do differently. Zoom in. So here we plot the values between 0.6 and 0.9. We can increase this a little bit. 2.1. Oh, it's also a little bit funny. 2.1. 1. Mhm. Increase a little bit. Actually, -2, right? Okay, that should do it. Good enough. Try one more time. Here we go. So what do we see? We see the blue curve plotted. That is our e of x, e to the power of x, shifted down to units. Then we see our first choice of x0 at 2. We see a dotted line, and this is where we evaluate the function and its derivative. We have the linearization, so we approximate this function as y equal nx plus n. And for y equal nx plus n, we can find the new root by following the inclination backwards, right? Back down to the crossing the root with the x-axis. So that is our new x1. Okay? When we go back, well, we actually measure the difference between function value and x. It's larger than our tolerance. So we choose a new x. That is now x1. And then we evaluate the function value and its derivative at x1. We do the linearization. We follow this again to the crossing or to the root of the x-axis. Now we get a new x. We evaluate, or we actually test what is the function value here. We test, do we hit our tolerance or not? We don't. So we do it one more time. Right? Again, we do the linearization, get an x3. But just now I told you we actually have 4x. So we should. We have 0, 1, 2, 3, right? 0, 1, 2, 3 of 4x. So we get in last x here. And that will be our solution, the root of the function, which is the crossing of the function with the x-axis, and that is 0.69. So how does this value compare to our bisection method? Is it very different? Is it very similar? Did we need a larger or smaller number of iterations? Does anybody see a difference to the bisection method? Is like the result the same? Is the type of result the same? So remember, with the bisection method, we only get an interval, right? We get, oh, your solution is between A and B. So the microphone is gone. So we only have, yeah, the YouTube video audio, right? Because otherwise, are you still hearing what I say? Can you still understand? Well, you all sit very far away, right? Which is okay, but so one of the differences is that the bisection method gives you an interval as solution. So you never get a specific value, you get a range. Your solution is between A and B. With the Newton method, you get one particular value that is determined to be your solution. Not an interval, but one value. So let's play around a little bit. We set a tolerance. We can always hard code and override the tolerance. So just now we had how much? 1 over 1,000? Is that right? No, 1 over 10,000. Let's lower this a little bit. Oh, I wanted to print this. So we can lower the accuracy, or we can increase the accuracy by lowering the tolerance. Just now we had a value 8.4 over 10,000. Now we have, how big is 10 to the power of minus 9? Well, 10 to the power of minus 6 is 1 over 100,000, right? So 1 to the power of minus 9 is 1,000 times smaller than that. So that would be 1 over 100 million, right? And we get this accuracy in 5 iterations. The value itself of x, that is our solution, hasn't changed much, right? We still get 0.693 as a possible function value. Sorry, solution of our function. Okay, are there any questions about Newton's method? So far, right, you have learned 2 solvers. One is the bisection method, one is the Newton's method, and you have implemented this, well, not you, but you have seen the implementation. They are very simple implementations in principle. Right, if there are no more questions or comments, then we continue after the break.